Well, it's a great pleasure to be here. I want to thank the Kavli Foundation. This week, when people have asked me why I'm here, and I say, well, I'm here for the Kavli Prize thing. And they say, so are you one of the winners? I say, sadly, there is no cookbook category. And you know, we really got to talk to the Kavli people about this. The other thing that's interesting to me is, as you may be able to tell by my name, my ancestors came from Norway. They left in 1868. But I look Norwegian enough that people on the street or in restaurants talk to me. And not only do I seem like a Norwegian, I seem like a not very smart Norwegian because I can't reply. Okay, so we're going to talk about an inside view of food. This is the cookbook that I wrote that was just mentioned. 6 volumes, 2,438 pages, a whole lot of other stuff. It was our attempt to try to do a couple of things. We wanted to have a comprehensive discussion of the science of cooking, the technique of cooking, and the art of cooking. I think all of those things go together. We also wanted to try to make the book interesting to look at so that it would get people who might think the science of cooking is a little bit off-putting, it's a little bit difficult, who would think, no, actually look at the pictures, it's kind of interesting, and the pictures would draw them in. And so we're going to look at a bunch of those pictures today, pictures that show us what happens to food while we cook it. But first, here are some fun facts about the book. 6 volumes, 2,438 pages, 1.1 million words. If you put those all into a single line of text, it would be 12 kilometers long. I'm not sure why you would like to do that, but I'm a nerd, so I like those kinds of numbers. We took 150,000 pictures and put 3,200 of them in the book. 1,522 recipes. Recipes from that include ours, plus recipes from about 72 of the greatest chefs in the world. 6 cooks. 44 writers, editors, and art staff, 19 kilograms unpacked, and my favorite statistic, 2 kilograms of ink. When the printers, you go to the printers to plan the book, they show you this blank book with blank pages. I said, well, how different it is? They said, well, it'll weigh more because of the ink. And I laughed. And they said, well, actually, on a full-page photo, the layer of the ink is about 1/1000th of an inch. Well, 1/1000th of an inch times a couple thousand, that's like an inch-thick block of ink. So 2 centimeters. We also have another book coming out soon. It's a thin little book, only 700 pages, 2 volumes. It's about cooking at home. So it has a somewhat simpler set of recipes that don't require as much exotic equipment. Here's where we made our book. This is our food laboratory. It's part of a general laboratory my company has where we build all kinds of new inventions, but we took part of it, we set aside, and we made this food lab. So now I'm going to talk about some of the scientific principles that govern how you cook. And of course, the most important part, the single most important thing you do in cooking is you heat food. We use the action of heat to modify foods to make them suitable for eating. And that heat comes in several different ways. The most important kind of heat transfer is called conduction, and it's governed by this partial differential equation, which was found by this man, Joseph Fourier. So we are the only cookbook in the world with partial differential equations. Fortunately, you don't need to be able to solve those partial differential equations through the recipes, but, you know, in another sense, you do. So suppose you have a steak that's 1 centimeter thick and another steak that's 2 centimeters thick, twice as thick. How much longer does it take to cook the steak that's twice as thick? You ask chefs, and chefs have got all kinds of different things. They'll say, well, it'll be twice as much because it's twice as thick. Or they would say, well, weigh it, and it goes by the number of pounds. In fact, because of this equation, you can do some simple mathematics to show it will scale roughly, not exactly, but roughly, as the square of the thickness. If you double the thickness, it takes 4 times longer to cook. Now, that's an example of a simple rule. It's simple to explain. It means if you want to cook things quickly, you must cut them into very thin slices. And there's different techniques in cooking that do that, but it's an example of a general rule that has got a lot of implications. Here's our barbecue cutaway, where we wanted to talk about how does the flavor of grilled food come from? We love the flavor of grilled food generally. Where does it actually come from? Now, one answer is that there's a lot of what's called radiative transfer. It's infrared light that leaves those hot coals that is mostly what heats the food, but it turns out that's not what makes the flavor. The flavor comes from the fat burning, those fat flare-ups. So here's a high-speed video. Now watch closely. This is an orange. And you see, what we're doing is we're taking a little zester, which cuts the zest of the orange. And there's enough oil in that orange that it makes that big flame. A tremendous amount of the flavor we associate with citrus comes from that oil. Well, in the same way, the fat that drops down onto a coal, here's fat dropping from a hamburger down onto a coal. Initially, it doesn't burn because it takes energy to vaporize, but then pretty soon it does. And when this fat flares up like this, it breaks a bunch of molecules in the fat. It's a process called pyrolysis. It's those compounds that are created that make the characteristic flavor of grilled meat. Here's another thing we did. We mapped what we call the sweet spot of a grill. So if you have a grill surface that's extremely hot, and it's radiating out infrared energy. The sun radiates infrared and visible light. That's partly how we get warm here on Earth. Well, at the edges of the grill, you don't get as much of the light as you do at the center. So we mapped this thing, and here's a page from the cookbook that shows what we call the sweet spot. The sweet spot is where the heat is even from one side to the other, even to within 10%. As you go to the very edge, it drops off very rapidly. So it's very hard to get even cooking if you move your food to the edge. So we thought about this a little bit. And if you've ever been in a department store, they have those mirrors that have 3-way mirrors. And if you look in the mirror and you look at one side, you can see a copy of yourself, infinite numbers of copies of yourself. So we decided to do that with the fire. If you put a reflective surface, a vertical reflective surface, now the entire grill is a sweet spot. And the reason is that the food sees, if you put your face there and you'd see an infinite number of copies of the fire because it gets reflected in the shiny grill. It's also why it's a bad idea to have your grill be black. Now, it usually gets black because of soot and you don't want to clean it. If you want your food to be even, you should always line it with like shiny aluminum foil because you're trying to reflect that infrared light. A black grill will never heat as evenly as one that has shiny sides. Here's some more about cooking with radiation. Broiling is like grilling. You're usually cooking from above. Now, the light that comes down is infrared light. It's too long a wavelength for us to see with our eyes, but it really is light. It behaves like light. In particular, it can reflect and bounce off things. And this is one of the reasons why it's very difficult to control the timing when you broil something. Because initially, 90% of the light in most foods is reflected. So it's only absorbing a little bit of the light. Most of the infrared light is bouncing off. But as that little bit accumulates and the food heats up, it starts to brown. Well, now in the middle here, only 25% is being reflected. Finally, only 10%. So here's an example with toast. Of course, the toast is very white to begin with. so most of the light reflects. So after 1 minute in the toaster, it's just a little bit brown. But now it's absorbing heat at a faster rate, so the process is accelerating. So after another minute, it's much more brown. And then 30 seconds later, and it's very brown. And finally, in another 15 seconds, it turns black, and if you left it there, it would catch fire. So the reason it's difficult to judge the timing is because it's a nonlinear process. It's out of proportion. The darker it gets, the faster the rate of heating goes up and up and up. It's sort of the opposite of what you'd want if you wanted to control things precisely. This is one of the reasons for a method of cooking called sous vide, where you cook at very low temperature. When you cook at a very low temperature, you have this opposite phenomenon. The closer you get to the temperature, the slower the process goes, so you can't overcook it. A lot of companies that make frying pans want you to buy a copper pan because copper conducts heat much better. And the really thick, heavy pans are much more expensive than the others. So we did a bunch of experiments and a bunch of computer modeling to understand how thick a pan you really need. So this is our thickest experiment. We just got a big 2 centimeter thick block of aluminum. And what we discovered is that no matter how thick you have the pan, the fact is that the side-to-side dimension is always much larger than the thickness, unless you had a huge cubical block of steel there. And so it actually makes much more sense to fit your pan to the burner, to the heat source, than it is to try to have a thicker pan. If you have a big pan on a small burner, you'll never get even heat, no matter what metal you make it out of, and really no matter how thick it is. Here you can see a very thick example. It's not even. It's only if you have the heat source and the pan of the same size that you can get even heat. Here's a classic problem that is used in thermodynamics classes. We actually tested it. Suppose that you get a cup of coffee for you and a friend, but you're waiting for your friend. They're going to be there for a minute or two. Should you add your cream right now, or should you wait until your friend shows up? What would have a warmer temperature later? Well, it turns out this is a very interesting problem, but first I've got a video to show. We have this wonderful camera, which takes 6,000 frames per second. So we can make these wonderful slow motion pictures. So it turns out that you always want to add the cream first. And over a period of 5 to 10 minutes, adding the cream first actually will result in your coffee being warmer by several degrees. And it happens for 3 different reasons. The first reason is that things that are hot emit infrared radiation. And the rate at which they emit goes as temperature to the 4th power. It's actually one of the few laws in all of physics that has something to the 4th power. So if you cool it down, it doesn't radiate as much. It turns out you also make it white. Things that are white don't emit as much radiation as things that are black. There's a whole topic in thermodynamics called black body radiation. A white body doesn't radiate as much. And the third reason is that the cream actually inhibits evaporation. We spent a lot of time in our book talking about the properties of water. And the reason that water is important is that most food is mostly water. There is more water in a cucumber than there is in a glass of milk. Now, that seems crazy, but in fact, a cucumber is about 95% water, whereas full-fat milk is about 5% fat, not water. And then there's a little bit of protein and other things, so it's just slightly less. Now, we're so used to thinking of a liquid and water, you think, well, of course milk is almost all water. Of course, a cucumber is this solid thing. No, a cucumber is almost all water. In fact, here you can see some common foods: a carrot, cucumber, bread, wine, bacon there at the side, that's 37%. Most meat is about 75%. So we like to say that food is basically water with a few extra contaminants in it. Now, that's important because water has some interesting properties when it freezes and when it boils. This is a picture I took in Greenland, and it's of an iceberg. Some icebergs are very white, some are very clear. We have a whole discussion in the book as to why that's true. Well, the first interesting thing is that this iceberg floats. Now, why should ice float? It turns out almost all substances, when you freeze them into a solid, are denser than they are in liquid form. Water is very strange, and it's strange because of hydrogen bonds. I won't go into all of the details, but water actually gets bigger when it freezes. That's why ice is on the surface. If that wasn't true, a lake would freeze from the bottom up, and then there wouldn't be any fish in it. And there's a whole variety of other things that would happen. Well, not only is it strange when you freeze it, water is even stranger when you boil it. This is the phase diagram of water. We're also the only cookbook in the world with phase diagrams in it. There's a principle among people who publish popular science books that each equation you add, your sales is cut in half. So I might have really had a great thing if I'd had fewer equations. I won't go into all the details, but what this diagram tells you is under which combinations of pressure and temperature is water a liquid, or is it a gas, steam, or is it a solid called ice? And understanding that is really important. Here's a very interesting effect. So watch this. This is something called the Leidenfrost effect. These are droplets of water on a hot skillet. If you've ever dropped a little bit of water, see how they dance around? The reason is they're floating. There's a thin layer of water vapor, and they sit there and they oscillate, and but it's not actually touching because there's a thin layer of steam. So they're floating on a cushion of gas. Here's an experiment we did with a steak, where we took a steak and we cooked it for various points in time. No matter how long you cook a steak from the bottom, you'll never cook it all the way through because food is mostly an insulator. The thermal diffusivity, that's the rate at which heat moves through meat, is actually very similar to wood. It depends on the wood, and it depends on how wet the wood is. But food is very much an insulator. So in this case, it's the same steak. You notice how it's puffed up a little bit in the middle? There's a period of time when it expands, and then later on it contracts. If you look in more detail, you can see that's the top half a millimeter. Most of the steak doesn't know that there's a pan there. It's perhaps a little strange talking about what a steak knows, but at the one edge is we call the desiccation zone. See, to make a steak brown, to make that brown color and the wonderful flavors that come from that, it has to be raised above the boiling point of water. But it's so wet, it can't go above the boiling point until it dries out. And so the whole point of searing a steak in a pan or a grill or other things is you're trying to dry out the surface enough that it can brown. But if you go just a half a millimeter inside the steak, you see how white it looks? That's not fat. That's actually what the meat looks like. If you have enough light and use a microscope, beef looks almost as white as chicken when it's cooked. A little bit grayish, but it's mostly very white. And in that region, it's boiling. And it's boiling because that's where the water is being driven out, and that's what causes the desiccation zone. In fact, there's little steam volcanoes that are happening, very much like a geyser, which is another Scandinavian thing from Iceland. Geysers are natural examples of the Earth's heat boiling water. And when you see all the sizzling in a pan and all those bubbles are the steam coming out of those little geysers. So as far as the rest of the steak is concerned, what we call the conduction zone, all it knows is there's some boiling going on. And then from that point inward, it's conduction that's carrying heat in. So I like to say we have two halves of the best kitchen in the world. These things don't work so well after you cut them in half, but it lets us illustrate what happens when you cook. So here's an oven and a home range that we cut, and we did this so both we can show how cooking on top of the stove works. We discuss what happens in the oven. It turns out one of the really important things in the oven is this same phenomena I mentioned. You know that when we get hot, I know this doesn't happen much in Norway, but when you go on vacation although this week I got sunburned in Norway, who knew? When you get very hot, you sweat. And the reason you sweat is our bodies, human bodies, cool ourselves by using the evaporation of water. If it's very humid, again, this probably doesn't happen much in Norway, but if it's in a sauna, it would happen, I suppose. If it's very humid, you feel much hotter because your body's unable to use that cooling. The same thing happens for food. A piece of meat is 75% water. When you put it in an oven, it doesn't matter what the temperature of the air is in there. It's always going to be at a much lower temperature because water is evaporating. If there's steam in the oven, that's different. Then it can't evaporate. That's like on a humid area. Now, in weather, meteorology, this is called the difference between a dry bulb thermometer. Here you see the thermometer on the top is dry, and the one below is wet. And of course, the wet bulb can never be more than 100 degrees C, the boiling point of water, and is usually, in fact, much less. Now, there are some ovens that can control humidity. This is a very fancy oven made for professional restaurants. The man, the head of the company that makes this oven came to our laboratory, and he said, what would it take to cut one of my ovens in half? And I think he was asking about what equipment I would use to cut it. But I answered him a different way. I'd say, I'd have to get one free. So he gave us one. We cooked with it, and then we cut it in half here. So this is this particular oven has a chamber of water underneath. So it can actually control the humidity as well as the temperature. That gives you better control over how the humidity and heat work together. Here's examples of chickens that we cook there, where we make the skin becomes incredibly crispy if you know the right temperature and humidity to cook it at. Here's a point I always like to make. People think, here's a teapot. People think that this is steam. This is not steam. This is steam. Steam is completely invisible. This, what you see up here is fog, or a cloud, or water droplets. You can call it many things. The steam is the part down here. And when the steam condenses, it takes a tremendous amount of energy. Or, when you boil water into steam, or you make water evaporate, it takes a tremendous amount of energy. And this is the man who really pioneered this. This is James Watt. Now, all of our electrical equipment in the kitchen has, this is this many watts and that many watts, or kilowatts if you have bigger things, 1,000 watts. We call them watts because of this man, but it turns out it was actually a food-oriented or drink-oriented thing that got him started. He was a professor at Edinburgh, and a Scottish distillery making whiskey hired him as a consultant. And they said, we've noticed that when we burn peat, it's pretty quick for the whiskey to come up to temperature. But then we have to keep putting peat in to distill it. Now, how come we're using so damn much peat? Well, this led Watt to understand something called the latent heat of vaporization. That's the amount of energy it takes to go from a liquid into a gas. And it happens for water that it's an enormous amount of energy is required. That's led Watt to improve the steam engine. It turns out he couldn't do very much for the whiskey folks. They still have to use a lot of peat. But it also is critical to understanding cooking. Here's one of our cutaway shots. Here we're steaming some broccoli. Now, which is faster, boiling or steaming? And so we set out to do some experiments about this. Here's carrots that are being boiled. On a general principles, you'd expect that steaming should actually be much more efficient. And for some shaped foods, it is. If you're steaming something smooth, like an egg, or in factories where they make canned food, they steam cans. And those cans are very smooth. But when it comes to something like broccoli, it turns out that boiling is actually faster than steaming. And the reason is that broccoli is very rough. It has this very rough surface. And because of the rough surface of the broccoli, it traps a layer of water. In boiling, the turbulence of the boiling water actually brings more heat in than steam does. That said, latent heat is a huge effect. So here's an experiment you should try, but don't blame me if you get burned. If you have your oven at home as hot as it will go, 200 C, 300 C, you can reach your arm in, no problem. You wouldn't leave your arm in there for a long time, but reaching your arm into an oven that's 200 degrees C is not a big deal. If you have a pot of water boiling, like for pasta, and you put your hand over it, you get burned right away, very seriously burned. The reason is that the air above the boiling water has steam in it. That steam will condense on you. It will transfer a lot more heat a lot more quickly than the air will. Air is actually a very poor way to conduct heat. It's useful for lots of reasons. We still like cooking in air. But if you can cook in a medium other than air, you almost always have a big advantage. The sous vide method of cooking I mentioned earlier, you typically cook in a bath of water. You have a large tank of water that's hot. And the reason you do that is that the water is about 1,000 times more dense than the air. And so it transmits heat vastly better than the air ever would. Now, steam is also the thing that puts the pop in popcorn. When water boils into steam, it expands in volume by a factor of 1,600. So if you had 1 liter of water and you boil it, it would make 1,600 liters of steam. So that's what leads to this. So watch this closely. I'll let it play once, and then I'll tell you more about it. So that's popcorn. So what's happening here is that the popcorn has water inside. Let me just... Okay, I'm going to do that one more time because it's fun. It has water inside. The water's boiling into steam. It's expanding in volume. A little crack opens, and this is now a steam rocket. You can't see it, but there's a little jet of steam shooting out. And it's trying to relieve the pressure. But what happens is it ultimately can't relieve the pressure fast enough, and the crack that started the rocket lets go, and the whole thing opens up. That's how popcorn works. Now, one of the ways that you can use these facts about water and steam is if you increase the pressure, you can make water much hotter than 100 degrees C and still be able to have it in liquid form. And that's what a pressure cooker is used for. So the higher the pressure, the higher the temperature. So at 1 bar extra pressure, twice normal pressure, water boils at 120 C. And then, of course, it goes up from there. Most pressure cookers work at 1 bar extra pressure, so they're at 120 C. Now, it may not seem like much, but that extra 20 degrees makes an enormous difference in how you cook. We have a recipe in the book for making risotto, which normally takes a long time. You have to carefully stir as you pour hot stock in. It's a wonderful dish, but it's a real commitment. You can make risotto in about 5 minutes in a pressure cooker. And it comes out really well. Here's another interesting thing. The reactions that cause food to brown are responsible for a lot of the flavor in foods. And there's several of these reactions. Caramelization is one of them. That's where sugars, particularly something called reducing sugars, will oxidize and turn brown, and they change flavor. Another set of reactions is called the Maillard reactions, after a French scientist. That's a combination of proteins and sugars that bind, that make browning. Now, normally, you have to have the temperature much higher than the boiling point of water for that to happen. But if you add a little bit of baking soda, which is alkaline, you can make the reactions happen at a lower temperature, just low enough that you can put it in a pressure cooker. So here we make these caramelized brown carrots by cooking them in a pressure cooker. And they actually brown all the way through because the temperature and the pH is such that, in fact, the browning reactions can occur. Now, the main reason that pressure cookers were developed were to kill foodborne bacteria. We have a whole section in our book on bacteria. We're probably the only cookbook in the world that does that. This is E. coli. Did anyone know it was so attractive? Now, E. coli is a dangerous food organism, but E. coli is actually very easy to kill. Almost any heat kills E. coli. The real problem in food-borne illness is this. This is Clostridium botulinum, botulism. And the problem with this is it forms spores, and these sort of bowling pin-shaped things are the spores of botulinum. They're very hard to kill. And so a man named Nicolas Appert, who invented canned food, discovered that if you used a pressure cooker and you cooked for a long enough period of time, you could actually kill these spores. Until then, in fact, any food that was sealed away from air had a chance of having botulism grow. In fact, botulinum comes from a Latin word for sausage. And the reason is that the Romans would make these sausages a little bit like a salami, so it was a hard, dry sausage, but they didn't know about this bacterium, and they'd often get very sick or even die from it. So it was the sausage illness. And it turns out that pressure cooking is how you can avoid that. Well, pressure cookers can also be used to tenderize tough cuts of meat. We do have lots of things in there. Here's one of our cutaway pictures where we show a pork roast. This is interesting. This is a very traditional cooking method. Although our book is called Modernist Cuisine, and we celebrate many of the modern advances, we also want to explain where cooking came from. So here we have a very traditional technique where you'd have a cast iron pot. You'd heat from below, but you'd also heat from above. Now, the reason you'd put those coals on above is you'd like some infrared, some radiant heat to come and brown the top of that roast. And today you call this braising, but today we don't usually use it with coals on top. We tried it. It actually comes out better this way. It's just a little more trouble in your kitchen. Another thing we spend a lot of time on in the book is understanding meat and muscle. Now, probably everybody knows that a chicken breast has very light meat. Chicken thighs have dark meat. But the breast of a duck is dark, so why? Well, it turns out whether you have light meat or dark meat depends on the amount of myoglobin. Myoglobin is a molecule that holds oxygen. It's similar to hemoglobin in your blood. The more endurance you need from the muscle, the more more myoglobin you need. A chicken is a ground living bird. If you chase a chicken, it will run before it ever flies. They hate to fly. They just fly as a short little hop to get away from something. So their breasts are white meat because the white meat muscle actually responds faster for a quick action, but has very little endurance. Ducks migrate. So for a duck to migrate, it needs to have breast muscles that are red. Now, in mammals, the same thing happens. Here's a pork leg. The interesting thing is, it's not that there's any part that's dark or light. If you look, It's how far it is from the bone. The closer to the bone, the harder the muscle fibers work. And the harder the work, the more it's important for them to have endurance. So here you see in this part of the pork, it's very light. As you get very close to the bone, it's very dark. So the same thing you find in a dramatic way on a duck versus a chicken, you find in different parts of the same pork leg. Here's an extreme case. This is seal meat. I took this picture in Greenland. Seals have to hold their breath for a long period of time. And because they have a long period of time, they have an incredible amount of myoglobin. Whale is very similar. If you in Norway you eat whale, very similar. You'll see it's incredibly dark because the myoglobin is required for holding its breath during a deep dive. Now, I won't go through all of this, but it turns out meat is very interesting. Meat is a little bit like your clothes, right? Our clothes are woven from various threads. And if you look closely at those threads, you'd find those threads are woven from even smaller fibers. If you looked at the cables on a big bridge, like the Golden Gate Bridge in San Francisco, those cables are very similar. There's tiny wires woven into bigger cables, woven into giant cables. Well, that's what meat is. And the difference between tender or tough cuts of meat depends on those fibers and on the molecules of collagen that are in them. Young animals or certain cuts of meat like tenderloin have one kinds of collagen. Older animals or very coarse-grained things have a lot more collagen. They're a lot more tough. Now, once you understand that, there's a whole bunch of things you can do. One thing you can do is you can use tenderizers. One common set of tenderizers is to use an acid, so a vinegar or lemon juice. The acid breaks a bunch of the protein molecules up, and that makes it more tender. Now, there's a few cuisines that, besides using an acid, will use a strong alkaline. And in fact, okay, here, let me tell you about this first. As you cook collagen, things change. By the time you get to about 60 degrees C, collagen shrinks up a lot. That's, if you watch a piece of meat cook, this is about 60 C is about the temperature where it starts turning from red to pink to gray. And you see lots of juice in the pan. Here's an example. Now, that juice is coming because you have heated up the collagen to a point where it's going to contract. And so the meat is actually wringing itself out. Its shrinkage of the fibers in the meat is causing it to pull against itself and force the juice out. So this is another one of the reasons that low temperature cooking is useful. If you cook the meat and never bring it above 60 C, you don't lose the juice. And in general, you'd rather, although this looks very appetizing, all the juice on the plate, you'd actually rather have the juice in the meat and then in your mouth. There's a similar phenomenon where I say if your kitchen smells really good, your food has lost something. All those wonderful flavors, if you'd cooked it in something sealed, those flavors would still be in your food. So I mentioned you could use acidic food. You can also use alkali, and one of the classic examples of using an alkaline substance to break up protein is lutefisk. And my cookbook has a recipe for lutefisk, and if that doesn't prove I'm Norwegian, I don't think anything will. So we actually have sous vide lutefisk, and it's very good done that way. So I thought I would tell you just briefly how we make these cutaway photos. The cutaway photos we came up with as a way to say, let's show people a magic view of what happens inside their pots and pans while you cook. What if you could see inside? Well, how do you do that magic? And the answer is we have a machine shop. This is right off our kitchen, and there are chefs in the world that have a kitchen as nice as ours, but none of them have a machine shop as nice as ours. So we cut things in half. It sounds a little bit silly, but the way we take these pictures is mostly we just cut things in half. Now, as you can see from this example, what we were do, or this example, you can't see it as this, perhaps you can see it better here. We've taken a sheet of Pyrex, a heat-resistant glass, and we have glued it to the pot. Now, the great thing is when you cut a pot in half, you have another half. So you photograph the one half just to get the photograph of the edge. Then you photograph cooking with this, and then you can do a little bit of Photoshop, and you put the two things together. It's very much like in a Hollywood movie when you have Spider-Man fly through the air. The actor or the stuntman has wires supporting them. And then afterwards, they digitally just take out the wire. So they're really flying, but the part that isn't real is that you don't have the you don't have the wire. Here, the part that isn't real is we have a piece of glass. Although in many cases, we don't have a piece of glass. So I showed you the picture of the coals. Well, if you put a piece of glass there, the coals would shatter the glass. So what you do is you just cut it in half and you leave it there. So I'm often asked when I say this, people say, well, what keeps the coals from falling? And the answer is Johnny keeps the coal from falling. We have one of our guys who was sitting there below there, and every time a coal would fall, he'd pick it up with tongs and put it back. When you cook with pots that are cut in half, you make a hell of a mess. But we had this motto: it only needs to look good for 1,000th of a second. What happens after that really doesn't matter. So if you're willing to make a really big mess, you can do this. Here's an example where we have cut a cream whipping, a foam making machine in half. So then here's our final video. This is opening a bottle of champagne. The person is pulling their thumb away as fast as possible here. And the thing I love about this is that all of the structure that you see, the oscillations and the pulsing and the turbulence, that all happens far too fast to see with the human eye. By slowing it down, or in the case of those other pictures, by cutting things in half, we can show you a vision of food you wouldn't see otherwise. And then based on that, help you both understand food and cooking a little better, understand the science behind it. You know, cooking is one of the few science experiments people do on a regular basis. And hopefully do a better job of cooking. Thank you.
Thank you.